Why did the lights just turn?
We just had a few slides with the red background.
Alright, so we're going to get this started. Today, Colin White is going to be talking about case-center clustering under perturbation resilience.
Right. Thank you, Nama. So I'm going to be talking about clustering, and this is joint work with Nina Balkan and Nika Hakdalab. This is in partial fulfillment of the speaking skills requirement. Okay, so this is a talk about clustering. Clustering is a fundamental problem in unsupervised machine learning. It shows up in many different places across many fields. So just a high-level overview, we're given a set of elements. And so say maybe our elements are articles. And all the articles have different topics. So some are about politics, some are about sports. And then all of these have different distances. You can think of two articles as being really close if they're very similar topics. But they might be really far apart if they're very different topics. So if one is about politics and the other is about sports. And then the idea of clustering is we want to partition all these elements into k different clusters. And somehow we want to minimize the distance inside every cluster. And I'm going to get more specific about that in a second. But there's just some way we minimize the distances. So this might be this might be a valid clustering. And so the way we do this minimization for all the clusters is by an objective function. This is a common approach. So you might have heard of common objective functions such as k-means, k-median, or k-center. And so this is going to tell us how we minimize these distances. Okay. So in this talk, I'm going to be discussing a specific objective function called the k-center objective. So now I'm going to describe a different example for this problem. So imagine you're designing a new city and you want to place k fire stations spaced throughout the city to minimize the maximum distance any fire truck has to get to any address in the city. Okay, so to be a bit more specific, we're given a set S of endpoints and a distance metric. And then we choose k centers from the point set S. And then we assign each house to the closest center. And so these are going to be our clusters. Now the objective, the cost of this clustering is going to be the maximum radius of any cluster. Okay, so for this example, the cost of this clustering is going to be this distance here. So I'm going to denote that by r star throughout the talk. Are there any questions about this problem? Okay. So I'm also going to be discussing a variant of this problem called asymmetric k-center. So this is almost exactly the same, but now we relax the condition that our distance metric is symmetric. Okay, so it might take 10 minutes to get from one fire station to a house, but it might take 30 minutes to get back. You can imagine rush hour traffic or one-way streets as where we might not want to have symmetry in real life. Okay, so everything else about the problem is the same. In particular, we still have the directed triangle inequality. So the distance from P to Q is less than P to R plus R to Q. And now we have to be a bit more specific in what we're actually minimizing. So we're minimizing the distance from the fire stations to the houses. We don't care how long it takes to get back from the house to the fire station. So we just have to pick a direction and be consistent about it. Okay. So these are the problems I'm going to be discussing. Okay. So what is known about these problems? So these are clustering problems. All the clustering problems I know, we can't find the optimal solution unless P equals NP. So we're going to be shooting for approximation algorithms. So in the 80s, Gonzalez came up with a 2 approximation for the symmetric k-center problem.
So does it mean input is a graph with distances, or what's input?
Yeah, a set of endpoints and a distance metric. So every point, there's going to be a distance. Any other questions?
And so this is for fixed K or for case and input?
K is an input, yes. Any other questions about the problem? Okay. So Gonzalez showed a two-approximation algorithm for symmetric K-center. So what that means is that given a clustering instance with an optimal solution R star, this algorithm will always return a clustering where the radius is 2R star, or the maximum radius is 2R star. And he also showed that this result is tight, so there does not exist a 2 minus epsilon approximation algorithm unless p equals np. So this kind of settles the symmetric K-center problem. Now, asymmetric K-center, turns out it's a bit harder. So it took about 10 years, and then Viswanathan gave a log star, O of log star n approximation. So if you forget what log star n is, it's the number of times you take the log of a number before you get down to 1. Okay, so for this algorithm, it returns at most O of log star n approximate, a clustering that's at most log star n times R star.
So distances are positive?
Yes. Yeah, for a distance metric, we assume all the distances are positive. Okay. So this is kind of a surprising result because log star n doesn't really appear that often in theory as the correct answer. But actually, it turns out it took another 10 years and a couple more papers, but it was actually shown to have a matching lower bound. So this is actually going to be a tight approximation factor for the asymmetric K-center problem. This is a nice, yep.
You measure the distances from the house to the fire station. In a way, does that these same results hold, or is that basically the same problem? Or is that a different problem?
Yeah, you can think of just every single pairwise distance, you reverse them, and then it's basically the same problem. Or it's a different problem, but you can just pick one direction and then you stay with that. Any other questions? All right. So just some side note, it's kind of interesting that this bizarre log star n function class was actually the right answer, the tight approximation ratio for this problem. It's kind of cool that log star n falls out of a natural problem. Okay. One more thing I want to point out is that on the one hand, for symmetric K-center, there's this really simple two-approximation algorithm. I'll actually explain it on the next slide. But for asymmetric K-center, it's a much more involved algorithm. It involves log star n iterations of this greedy set covering operation. So it's much more complicated. Okay. So now just kind of as a warm-up, I'm going to explain the two approximation for symmetric K-center. So we're going to start out, we're just going to assume we know the optimal radius, R star. We can make that assumption because if we don't know it, well, remember from a few slides back, it's just going to be a distance between two of the points. So in the worst case, we can just keep trying different distances until we happen to guess the right one. It'll only add some polynomial factor to our algorithm. So now we iteratively do the following. We pick any unmarked point, and then we mark all points distance less than or equal to 2R star from that point. And then we just keep doing this over and over until all points are marked. So I claim that the clustering returned by this procedure actually has cost 2R star. And the way we can see that is you can actually prove that after t rounds of this procedure, we've pulled out t clusters from the optimal solution. So if that were true, then this would terminate after k rounds. And we know that everything's 2R star from its center, so this would be a two approximation. And so this isn't too bad to see. So if you imagine some point that we pick, we know by definition of R star, it's at most R star to its optimal center. We don't know the optimal center, but we know it has to be R star away. And then we also know that this center has to be R star from every point in its optimal cluster. So say this dotted region is the optimal clustering. So then by the triangle inequality, we know that the point we picked is at most 2R star from its optimal cluster. So that guarantees that this point will pull out its entire cluster. And so then every new round, we pick a point that must have come from a different cluster, otherwise it would have been marked. And so we can get this inductive analysis. Any questions about this algorithm? Yep.
How did you guess the R star?
Yeah, so you can imagine, so now we have the full algorithm, assume we don't know R star. So we only have n squared many choices. So we can just try all choices. Sometimes it might return nonsense, other times it might return, bad clusters. But we just look at all the answers we got and take the valid clustering that's the best. Okay. And for the rest of the talk, I'm actually going to assume we know R star. Okay. Any other questions? All right. So now you might be wondering, like, I explained these problems, and then I showed they're completely settled. But in this talk, I'm going to be explaining a new model called Perturbation Resilience. And I'm going to show results for this new model. So I'm going to get way more specific in a second. But you can think of Perturbation Resilience as kind of trying to model real-life instances better than these worst-case approximations we get. And so it's kind of motivated by more real-life instances. OK, so what do I mean by this? So there's this cool line of work called beyond worst-case analysis. And the intuition here is that these non-constant approximations aren't really the best thing to have in real life. And also, we have these NP hardness results that show we can approximate to this factor. But often these proofs involve really intricate constructions, and they're always really brittle. And so maybe in real life, we're never going to see these complicated constructions. So maybe we can prove better results in more real-life instances. So a famous example of this is the Simplex algorithm. Although it technically can run in exponential time over a worst-case input, in practice, we almost always see it running in linear time, or close to linear. And so there's this really nice work by Spielman and Ting, which kind of shows a smooth analysis assumption that shows that it always runs closer to linear if we look at a more smooth version. Okay. So in this talk, I'm going to be discussing an assumption called perturbation resilience. So this is going to be a promise condition. I'm always going to have a clustering, and I'm going to assume it satisfies perturbation resilience. So the idea here is that if we have some clusterings, if we have some points, and we kind of change the distances by some factor, then the optimal clustering should not change. Okay, so look at the data set on the right. All the points are like really bunched together. So maybe we'll pick this clustering here for the optimal solution. But maybe if we change just a couple distances, the optimal clustering is going to change drastically to this. Okay, but if you look at the data set on the right, all the clusters are a bit more spread out. So maybe if we change some distances, the optimal clustering does not change. Okay. And just as maybe some justification for this assumption, we can, if we're trying to cluster and our data set looks like that, maybe the clustering that technically minimizes our objective function isn't really that meaningful. Whereas if the clusters are more spaced out, then we kind of get a more meaningful solution. If you think of the articles I was clustering on the first slide, we would get like politics, sports, technology. Whereas over there, we would get these vague topics that don't really have a meaning. Okay. Any questions so far? So now I'm going to get more specific in how we define this. Okay, so given a clustering instance, I'm going to say an alpha perturbation is a new instance with the same set of points, but a different distance function. And in this distance function, I'm allowed to stretch out all the distances by at most a factor of alpha. Okay. And then an instance satisfies perturbation resilience if for all of these perturbations I can do, the optimal clustering stays the same as before perturbing it. Okay, so if we look at these two clusterings, on the one hand, if I change the distances by a little bit, the optimal solution will change. So this one does not satisfy perturbation resilience. But for this one, the clusters are more spread out. So it is going to satisfy perturbation resilience. And just one more note about this definition. It's OK for the optimal centers to change. So maybe for this cluster, if we move some of the distances, the center is going to change, but the clusters remain the same. Yep.
Why? So you can stretch out edges here, but why? Like you could also imagine a definition where you have contracted edges as well.
Yeah. So if you think of the clustering problem, say we multiply all the distances by a factor of 2, it's not going to change the clustering problem. So we can kind of, without loss of generality, just assume that we're only increasing distances. Yeah. So if we're allowed to contract, it'll just be the same thing. Any other questions about this definition? Okay. So now I'm just going to give a bit more intuition for kind of how this line of work works. So if alpha is really low, it's kind of not giving much more structure to the problem. So if alpha equals 1, we have no more structure at all. It's just like regular clustering. But say alpha equals 100, then our clusters are going to be really spread out, and the problem is going to be really easy. So as I said before, this is a promise condition. We're just given a clustering instance, and we know that we're going to assume we know it satisfies this assumption. And so our goal is to find an exact algorithm for clustering. So no more approximation algorithms anymore. And we're going to see is how small can we make alpha and still get an optimal algorithm. So that's our goal. If alpha is 100, it's easy. So we want to know how small can we make it to get this optimal algorithm. Okay. So what is some prior work for perturbation resilience? So Bilu Linial defined perturbation resilience in 2009, and they studied max cut, and they showed under root n perturbation resilience, you can get an exact algorithm. Then here at Carnegie Mellon, Awasi, Blum, and Sheffet studied algorithms for center-based clustering and showed an algorithm under 3 perturbation resilience. So center-based clustering is a more general term. It captures k-median, k-means, as well as symmetric k-center. Okay. So this result was improved a bit later by Balkan and Liang, and they showed a new algorithm that, assuming 1 plus root 2 perturbation resilience, gives an exact algorithm, again for center-based clustering. And then there are more results for max cut, lowering the level of perturbation resilience needed, and also minimum multi-way cut. And then a very recent result by the Makaricha brothers improved on the center-based clustering once again. So now the perturbation factor needed is just 2. Okay, so in this talk, we're going to show algorithms for symmetric and asymmetric k-center under 2 perturbation resilience. So on the one hand, just for symmetric k-center, this is dominated by this result, but we're the first result to handle asymmetric k-center. Okay. And then we're also going to show that this result is tight according to the level of perturbation resilience needed. So if you only assume 2 minus epsilon perturbation resilience, then the problem remains hard. Okay.
This is more or less for all of these things, or the hardness?
This is for symmetric and asymmetric k-center. Yeah, so for instance, for k-median or k-means, we don't know any hardness. Okay. One other thing I want to point out is that some kind of cool feature is that for the asymmetric k-center problem, in the worst case, there is a non-constant approximation ratio, and that was tight. But we only assume a constant level of stability to get an optimal algorithm. And this is actually the first time this has happened, because if you look at maybe max cut, another problem with no constant factor approximation in the worst case, you also need to assume a non-constant level of stability. Okay. Okay, so now I'm going to get into the results. So I'm going to start with symmetric k-center, and then I'm going to move to asymmetric k-center, and then just talk about the hardness, and then talk about some more robust versions of the definition. So for symmetric k-center, the theorem we were able to prove is actually more general than I made it seem a minute ago. We can actually show that given a clustering instance that satisfies two perturbation resilience, any two approximation algorithm you run will actually return the optimal solution. So the proof is not, yep?
So my intuition, which is probably wrong, is that this is true for any problem, and if you replace 2 with any other constant.
Yeah.
Is this something that's very specific to this problem and 2, or more general?
Definitely, you can replace 2 with anything. So once I prove this, we'll actually have an algorithm under log star n for asymmetric k-center. So the 2 is not specific. I'm not sure about other problems, because we've only done this for clustering, and there's a chance there's something kind of subtle going on for clustering, but that would be good to check if this holds for max cut or some other problems. Okay, any other questions? Okay, so the proof I can actually fit on a single slide. So here's the proof. So we're going to start with a 2 perturbation resilient instance and say the optimal solution is r star. And now just pick any 2 approximate solution. Okay, so what we're going to do is we're going to prove that this 2 approximate solution is actually the optimal solution. So how am I going to do that? Well, I'm going to construct a 2 perturbation d prime. And I'm going to construct it in a specific way. So first I'm going to multiply every single distance in the graph by a factor of 2. And then I'm going to look at the distances that were in C. So if there's a point and its center in C, then if that distance is greater than 2r star, I'm just going to shrink it down until it's exactly 2r star. So remember, these distances in C are at most 2r star to begin with. So this will still be a valid 2 perturbation, even after doing this step. Okay?
Maybe I just understand. So first you take absolutely all the distance and multiply by 2.
Yeah.
Then you truncate the distances which are greater than r star.
Greater than 2r star.
2r star, but this may change it by a very large factor.
But only the ones in C, and we know the distances in C are at most 2r star to begin with.
What do you mean by in C?
So what I mean by in C is a point, and it's the distance from a point to its center in our 2 approximations C.
I see.
Okay. So these ones we're guaranteed are at most 2r star. So then we're never going to truncate a distance to be lower than it was from the start of the problem. Okay. All right, so I define this 2 perturbation. And now I'm going to claim that our 2 approximation C is actually optimal in this 2 perturbation. So there are 2 things to prove. So first is that C is still costs less than or equal to 2r star. So the reason that's true is that it was less than or equal to 2r star at the start. And then I multiplied these distances. But if anything in C was greater than 2r star, I shrunk it till it was exactly 2r star. So C is going to have cost 2r star. And now let's look at any other clustering. I claim that any other clustering has cost greater than or equal to 2r star. The reason that's true is because if we take any other clustering, it's greater than or equal to r star at the very start, by definition of r star. And then we multiplied all distances by a factor of 2. So now any other clustering has cost greater than or equal to 2r star. Yep.
So do you have to maintain that d prime is a metric when you're doing this perturbation? Because it seems like you could this perturbation and end up with something that's not a metric.
Yeah, that's a good question. So for this work, we were not able to assume that d prime is a metric So you can actually stretch out distances and it won't satisfy the triangular inequality anymore. But there's actually some exciting recent work that's actually able to handle this problem. So a good follow-up question is, do our results still hold under that added assumption? Any other questions?
So your assumption is that the approximation algorithm also works for input is not a metric. Is it?
So the assumption is that we're given some clustering instance, and then we're allowed to stretch out the distances, and we can even stretch them out in ways where it will not be the triangular inequality.
Right, so the theorem is that two approximation algorithm has to work, even if it's not a metric.
No, so our clustering instance, that has to be a distance metric, but this two perturbation resilience assumption. If you look at the assumption, remember I was talking about perturbations? The perturbations, yeah. So this d prime that I'm doing, maybe that's not a metric. Okay, so I was in the middle of the proof. So we just showed that c is cost less than or equal to 2r star. Anything else is greater than or equal to. So that means that c is optimal under this perturbation I constructed. And then by perturbation resilience, it had to have been optimal at the start. Okay. So that's the whole proof for symmetric case center. Any questions before I move to asymmetric case center? Okay. So this problem is going to be harder. I'm just going to show a specific algorithm that'll handle clustering under two perturbation resilience. So I'm just going to start with some intuition. So in the asymmetric version, there are these really difficult points where the distance from the center to that point is much smaller than the distance from the point back to its center. It turns out these are going to be the trouble points because they can kind of go really close to other optimal clusters. So it'll make it really hard for us to distinguish the optimal clusters. Okay, so it would be really nice if we could find a subset of points that behave more symmetrically, that are the good points. So that would be really cool if we could only work over the good points. So that's going to motivate the following definition. I'm going to construct a set A, and a point P is in the set A if for all other points Q, if the distance from Q to P is less than or equal to R star, then P to Q has to also be less than or equal to R star. So this would be nice because it's kind of the points are symmetric over the distance we care about, which is R star. But some question you might have right away is, what if this set is empty? How do we even know? What if we have a really asymmetric instance where none of the points satisfy this? Okay. Well, it turns out we can actually prove nice facts about this set A. So the first nice fact we get is that all the centers from the optimal clusters have to be in this set A. So not only is the set non-empty, but there's at least one point from every optimal cluster in the set A. Of course, there might be other points in the set too. But we can prove another nice fact. And the second fact says that any point outside A belongs to the same cluster as its closest point in A. So that's kind of a mouthful, but I think it'll be easy if I show a picture. So say these white points are the points outside the set A. I'm going to draw an edge to their closest point in the set A. And then if you look at the optimal clusters, there's no edge in between each cluster. So if 2 points have an edge, then they're in the same optimal cluster. Yep?
This is closest in the sense of going from the point not in A to A.
Yeah, that's a good point. I'm kind of putting the details under the rug for a couple things, but you're correct. It's from the point outside A to the point in A. So these two facts actually imply a really powerful statement. So it turns out that these two facts kind of reduce the problem to just clustering within the set A. Because if we find an optimal clustering over the set A, then all we have to do is attach the points outside A to their clusters from the points inside A, and then we'll get an optimal solution for the entire problem. Okay, so now we're doing pretty good. We only have to work over this symmetric set A. But there's still some more work to be done. So on the next slide, I'm going to explain a couple more useful properties. And then I'm going to show how these imply an algorithm for the whole thing. Okay, so the first property we get is look at some cluster. Any point outside this cluster is distance greater than r star to the center of that cluster. So I won't have time to prove these properties, but just some intuition as why it's true. I can construct another perturbation, just kind of like that other proof I showed, and I'll get a contradiction unless this is true. Okay. So we also get another property. If we look at a cluster, and at any point in this cluster, the distance from the center to that point is always going to be less than the distance from points outside the cluster to that point. This was actually proven in previous work, but we show it's also true even for asymmetric instances. Okay. So now I'm going to get to the key observation that'll kind of immediately imply an algorithm. So what I'm going to do is I'm going to look at balls of radius r star around all the points. So I'm going to start by taking a ball around a center, an optimal center. So if we look at this ball, by definition of r star, it has to cover the entire optimal cluster. But also by property 1, we know that points from other clusters have to not be in this ball. So it actually gets exactly the optimal cluster here. But not only that, it also satisfies this nice property by property 2, where every single point in this cluster is closer to its center than to points outside the cluster. So I'm going to call that margin property. So it's kind of like a nice separation property of this set. Okay. Everybody good so far? So now let's do the same thing, but around a non-center. So I'm going to take any non-center and draw a ball of radius r star around that point. So maybe it'll contain some points from different clusters. But it turns out we're going to be able to recognize that, because those points are closer to their own center than to this other point. And the optimal center for that point has to not be in the set by property 1. So these two properties kind of give us this way of detecting whether a point is a center or a non-center. One thing to note is that if this ball does not contain any points from another cluster, then it might satisfy margin. But then we know that it's a strict subset of its optimal cluster. So maybe that's still like a good case for us. Okay, so the takeaway from this slide is that balls around centers satisfy this cool property called margin, where balls around non-centers might not satisfy the property. Okay. So now I'm just going to describe the full algorithm, and then on the next slide I'm going to give some ideas as to why this is correct. So we're going to start by just creating the set A. So if you remember from the definition a few slides back, it's actually easy to do this in polynomial time. And for now, I'm just going to erase all the points outside of A. We're not going to deal with them for now. Okay. So now for every single point in this set A, I'm going to construct a ball of radius r star. And then in the next couple steps, I'm going to prune some of them out. So first, I'm just going to look at every ball, and if it doesn't satisfy this margin condition, then I'm just going to cross out that ball. And then in the next step, if I find two balls, and one of them is just a strict subset of the other, then I'm just going to get rid of the smaller one. Okay, so I'm going to do this for all the balls, and a lot of them are going to be crossed out, some of them are not going to be crossed out. So I take the balls that are not crossed out, and now I'm going to bring back the points that were outside the set A. And I'm just going to attach those points to the same ball as their closest point in A. And then I'm going to return the the sets that we just constructed. Okay. Any questions about this algorithm? Okay. So now I'm going to get into a proof of why it's correct. Okay. So what I'm going to claim is that we make these balls and then we prune some of them out. So I'm going to claim that after the pruning steps, we're only left with just the optimal clusters. So that kind of follows from the key observation I had on the last slide. So if we look at the ball around the centers, those are going to be the optimal clusters, and they're going to satisfy this margin condition. So they're not going to be deleted in step 3. But if we look at balls around non-centers, if they contain points from other clusters, they are going to be deleted in step 3. The other case is if they're just strict subsets of their optimal clusters. But then they're just going to be deleted in step 4, because we have the optimal cluster, and then if we have a subset, then we're just going to delete the subset. Okay, so the final case is if we get lucky and there's a ball around a non-center that actually covers its optimal cluster. But then we're just going to have 2 identical sets. So it doesn't really matter which one we pick. We're just going to keep one of them, and it won't get pruned out in the step 4. So any questions about how we show that, how we prove this, the optimal clusters are the ones that remain after the pruning step? Okay. So now we're doing pretty good. And then as I explained a few slides before, once we optimally cluster the set A, all we have to do is attach all the points outside A to their closest point inside A. And then those clusters will be optimal over the whole instance. So this actually is an algorithm for the entire clustering instance. Okay. So this completes the proof of the algorithm. Any questions about this? Okay, so yes.
So maybe, like, imagine that when you do this perturbation, you have a very small number of points which clusters. Can that totally break this, or can you somehow salvage the same idea if you have a very small number of, promise at most 2 switch or most 10 switch or something?
I'm sorry, are you?
Switch clusters.
What is very small? Oh, you mean only 2 points can switch clusters?
Yeah, I mean there's some small number of switches. I mean it's most, but you know there's this 1 point in the middle. That,
yeah, I'm actually going to have a slide on that
right.
in a couple slides. Okay. Any other questions? All right. So now I just wanted to point out this cool fact. So I showed algorithms for symmetric k-center and asymmetric k-center, both under 2 perturbation resilience. But if you remember from the start of the talk, these problems were like drastically different levels of difficulty in the worst case. Symmetric k-center had an easy 2 approximation, whereas asymmetric k-center had a O of log star n approximation. So it's kind of interesting that these problems, just assuming this mild stability assumption, all of a sudden we get optimal algorithms. And pretty soon I'm going to show a hardness result where this level of stability needed is actually tight. So what we get is that asymmetric k-center and k-center are equivalent in difficulty with respect to perturbation resilience. It's just kind of surprising that we get the stark contrast between the worst case and beyond worst case. Okay. So now I'm just going to quickly talk about the hardness result, and then I'm going to talk about more robust versions of perturbation resilience. Okay. So the lower bound we get is that there's no polynomial time algorithm to find the optimal solution for symmetric k-center unless np equals r. Symmetric k-center under 2 minus epsilon perturbation resilience. And since this is a lower bound and symmetric k-center is a subset of asymmetric k-center, we get the same result for asymmetric k-center. Okay, so I don't have time to get into specifics, but I just wanted to explain that you can kind of think of alpha as a spectrum where on the left, if alpha equals 1, we have no structure at all. So what this lower bound implies is that even for alpha really close to 2, we still don't get an optimal algorithm. So it's kind of no better than just assuming nothing at all. But then earlier I said that exactly at alpha equals 2, we can get an efficient algorithm. Yeah.
So I was saying basically if I have 2 minus epsilon perturbation resilience, I will not only exactly, I will not even have a good approximate algorithm.
No. So I'm only claiming there's no exact algorithm.
But there possibly is some trade-off between perturbation and resilience. Okay.
Yeah. Okay. So I guess I should be really specific. When I'm talking about no structure, I mean no structure with respect to finding an exact algorithm. So maybe there is structure for getting an approximation. That's a good question for kind of follow-up work. Okay. But just what this result implies is we actually find the exact value of alpha for which the problem switches from being hard to finding an efficient algorithm. So we know exactly where this alpha is. Okay. And then for alpha much greater than 2, the problem kind of becomes trivial. Okay. So any questions about this lower bound? Okay. So now I'm just going to talk about some more robust definitions. So as was pointed out, under alpha perturbation resilience, the clusters can't even change a tiny bit. Every single point has to be in the same optimal cluster. So we also have this more relaxed definition called alpha epsilon perturbation resilience. So what this says is that the optimal centers can change, but only by a little bit. So say we have some optimal clustering here, and we do some perturbation, and the new clustering is like only a tiny bit different. There are only epsilon endpoints that switch clusters. There's actually kind of a rigorous way of showing the distance between 2 clusters, but I don't have time to get into that. Okay. So now we kind of have 2 parameters we can turn. We can change to make this assumption weaker or stronger in any way we want. So we also have results for this more robust version. So for symmetric case center, we have an algorithm assuming 3 epsilon perturbation resilience. And the one thing is that we need a lower bound on the optimal size, or the size of the optimal clusters. So all the clusters have to be at least epsilon in size. And it turns out we need that condition, because if it's not true, then the problem is NP hard. And we also show an algorithm for asymmetric case center, assuming 4 epsilon perturbation resilience, with the same assumption about the lower bound on the optimal cluster sizes. Okay. Any questions about the robust definition? So I don't have time to get into the algorithms, but I encourage you to look at the paper if you're curious. Okay, so now to just conclude. So I showed polynomial algorithms for both symmetric case center and asymmetric case center under 2 perturbation resilience. And now from a theoretical point of view, it's kind of cool because, as I explained before, it's the first problem for which there's no constant factor approximation in the worst case, but just assuming a constant level of stability, we get an exact algorithm. And this is also the first tight result with respect to the level of perturbation resilience needed. And it's also kind of cool that these 2 problems, they're different levels of difficulty in the worst case, but just under this mild assumption, we get exact algorithms. And we assume the same level of stability. So they're kind of equivalent in difficulty. Okay, from a practical side, maybe it's not quite as interesting, because there's only a small window of values of alpha for which the problem is interesting. If alpha is less than 2, we know there does not exist an optimal algorithm. But if alpha is greater than 3 or so, then the clusters become really spread out, so it kind of makes the problem trivial. So there's only really between 2 and maybe 2.5 where the problem is interesting. Okay. So now just a couple open questions. So before a month ago, I would have said, can we do the same thing for k-median or k-means? But that's actually been proven. But there's still no lower bounds for this. So it's still a good question, can we go beyond 2 for k-median or k-means? We know k-center is completely done now. Another open question is, can we apply this technique of symmetrizing the instance to other asymmetric problems? So it'd be really cool if maybe we can do this for asymmetric k-median or something. Okay, thank you. Yep.
Was this permutation resilience observed in practice, or is it more of a theoretical construct?
Yeah, so it's actually NP hard to test whether a clustering instance is perturbation resilient. So right now it really is more theoretical work, motivated by real life. But maybe one more thing I could add is that, as I was explaining when I introduced the assumption, it's kind of like if a clustering instance doesn't have perturbation resilience, then the clusters aren't that meaningful. So you could maybe make an argument that whenever you want to do clustering meaningfully, then you're going to want to have this assumption.
Do you think anything could be done with an additive kind of perturbation instead of a multiplicative?
So there actually is work on that, but it's kind of tricky how to nail down what you mean by additive, because you can always blow up your clustering instance and it'll stay the same problem. So there is work that tries to do that, but in some sense it might be a bit cleaner to deal with multiplicative versions. Yep.
So you gave one sentence where the log star came up in the upper bound of the approximation. Can you give one sentence somehow where how does log star appear in the lower bound?
So it's this reduction from a gap instance of hypergraph coloring, I think. And I know the upper bound has these log star n procedures of greedy set cover. I'm not too familiar with the actual reduction in the lower bound. Any other questions?
Yeah, so did you gain anything if you assume the points are in the plane with Euclidean distance rather than just general triangle inequality?
Yeah, we don't. Okay, so our results hold for any distance metric. So are you asking, do we get better results if we also? Yeah, so we don't have any results for assuming they're in the Euclidean plane. That could also be interesting follow-up work. Maybe we could, it's kind of more natural for k-means to assume Euclidean space, so it'd be interesting to see if there's more we can do for k-means.